So in the last video, we talked in some detail about why measurement error is always, one reason why measurement error is always possible, and that is because perceptual error is always possible. And the reason why perceptual error is always possible is because your brain has to use all sorts of clues and tricks to try and figure out what the world is like given the stimulus to your sensory apparatus. And given that measurement error is always possible, there shouldn't be certainty in science because science begins with measurement, with observation. Another reason why measurement error is always possible is because it's always possible that your sample of the world, the portion of the world you're observing, is not representative of the world. And that can happen just by chance. So let's take a really simple example here. You have the universe here and an observer on Earth observing the universe, and based on that observer's observations, the observer concludes that the speed of light is uniform. And over here you have someone who can observe a much bigger portion of the universe. And based on those observations, that other person concludes that the speed of light isn't uniform. And, it's the best theory you could come up with, given the portion of the universe you're observing over here on the left, is that the speed of light is uniform. But if you have a bigger sample, if you've observed more of the universe, you see that it doesn't operate the same in all places, and therefore it's only the sort of provincial view that leads to the conclusion that the speed of light is uniform. Now, I think that's implausible. I think the speed of light is uniform. I think our sample is big enough to justifiably believe that, to conclude that it's true. But it's possible we're wrong. We haven't observed the entire universe. Another reason why measurement error is always possible is because theorizing often goes into measurement. So, for example, observations of distant planets presuppose theories of how telescopes work. After all, we don't observe those distant planets directly, we observe them through telescopes. And in order to make sense of the observations we make when using telescopes, we have to have some opinion, some theory about how exactly telescopes work. And the theory about how telescopes work presupposes theories about how mirrors work. And those theories about how mirrors work presuppose theories about how light works. And this point will become important when we think about confirmation and disconfirmation, but I'm going to leave it there for now. Here's an example in which theorizing going into measurement in a kind of direct, crude way played a big role in leading to a mistaken conclusion. So in the mid-1980s, every model of ozone depletion agreed that existing levels would be above a certain threshold. That is, even the models that predicted the most severe and dangerous depletion of ozone predicted that levels would still be well above that mark. So the satellites sent into the stratosphere to measure depletion were programmed to dismiss any measurements below that threshold as errors. So they would record that there was an error, but they wouldn't record the details. Scientists had seen many of these errors during measurement over the Antarctic, and they presumed that the satellite was wrong. There was something wrong with the satellite because it was just recording too many errors. Ground measurements, which are generally less reliable than satellite data, suggested that the levels were, in fact, below the key threshold, which everybody agreed levels could not be below. And some people argued, based on the ground measurements, that we were in fact reaching dangerous levels of ozone depletion. And many others dismissed such arguments, noting that the satellite data is much more reliable, and these satellites that were getting these measurements over the Antarctic, suggesting that levels were so low, were just faulty. Well, it turned out the ground measurements were correct, and the satellite wasn't faulty. They reprogrammed the satellites and sent them up to actually record levels below, rather than just registering errors, record levels below what they thought was the minimum threshold, and it turned out levels were in fact below that minimum threshold. So the background theories that predicted that levels were above that threshold were false, and they were used to design the instrument by which we measured, and consequently our measurements were unreliable. So the background theory made accurate satellite measurements impossible. Okay, so there's a straightforward example. Incidentally, this story has a happy ending. This was in the 1980s during the Reagan administration, and the Reagan administration, to their credit, decided that this was a serious problem and took steps to prevent the pollutants that were leading to depletion of the ozone, and the things have stabilized. So good for them. next, independent reason to think that there's no certainty in science is that observation always underdetermines theory and theory always underdetermines observation. Now, right now, those are just slogans. There's no reason why you should understand what that means. When we talk about theory confirmation and disconfirmation, we'll talk about this in detail and you'll come to understand what that means. But we're just going to set it aside now. Okay, we're going to stop this video there. And in the next video, we'll talk about the goal of science.